Hello, this is Jack Jackson. Today we're going to be talking about the law of cosines. As usual, I'm using my Trigonometry Ultimate Sketch, and we're going to be using the law of cosines page. So here's the actual result we're going to prove, that c squared equals a squared plus b squared minus 2ab times cosine of angle C with our standard labeling. And if you may notice that the first part of this is just like the Pythagorean Theorem, and in fact this is an extension of the Pythagorean Theorem. And we're going to be using the Pythagorean Theorem quite a bit in our derivation and proofs. So let's go ahead and prove this result. So we're going to start with any triangle ABC, and as we usually do with our labeling, we're going to let the uppercase letters A, B, and C stand not only for the vertices, but also for the measures of the internal angles at those vertices. And let the measures the opposite sides of these angles be labeled with the corresponding lower letters. So A is the length of from B to C, it's the length of the side opposite angle A. B, lowercase b, is the length AC, which is the length of the side opposite angle B, and little c is the length of the side opposite angle C, which is, of course, the distance A to B. And we're going to construct an altitude from A perpendicular to line BC, and it will go through point D on line BC, and let H be the distance from A to D. And there are going to be 4 cases to consider, and we have a dynamic illustration on the right for each case. So case 1 is where D actually equals the point C. So when we draw this perpendicular, we see that we actually have a right triangle here. Well, in this case, angle C and angle D are both the right angle there. This is BA. Okay. So notice that cosine of angle C is the cosine of pi over 2 radians, or cosine of 90 degrees, which is 0. So c squared equals a squared plus b squared, basically minus 0, from the Pythagorean Theorem. So this does still work here because this cosine of C is 0. So the easiest case, I guess, is when the angle C is a right angle, that this degenerates exactly to the Pythagorean Theorem. Now in case 2, suppose that we have CDB. What this means is that D is between C and B. So whenever we draw this altitude, it lands on this line segment CB, where D is between C and B. So the picture looks kind of like this. And this is dynamic, so I can move this around and get various different size objects. I can move this around, but they all stay with point D being somewhere in between here. Okay, so that figure shows case 2. Now let's look at this case. Notice that we have 2 smaller triangles which are right triangles. Triangle ACD, and then also triangle ABD. So we have 2 right triangles. And it must have at least 2 acute angles, so angles C and B must be acute angles. And so let's let X be this distance from C to D, and then of course A is the distance from C to B, so that makes A minus X the distance from D to B. Now we're going to apply the Pythagorean Theorem to each of these smaller 2 right triangles, so we can apply the Pythagorean Theorem. So in this triangle ACD here, we get B squared equals X squared plus H squared. And for the other triangle, we get C squared equals H squared plus A minus X squared, which is what I have here. Now we're going to solve the first expression for H squared. So we just subtract X squared from both sides, and we get H squared equals B squared minus X squared. Now take that value for H squared and put it in place of the H squared in the other expression. So B squared minus X squared goes in place of this H squared in the other equation. So we basically put our 2 equations together there and eliminated the H. Now we're going to use a little bit of algebra here. A minus X squared is A squared minus 2AX plus X squared. That's essentially a distributive property, or you may know it as FOIL. And we multiply that out and we get that. and we still have our b squared minus x squared. Combine like terms here. Let's see. Well, we don't exactly combine like terms. What we're going to do is, yeah, we do combine like terms. The x squared and the minus x squared cancel. And so you're left with a squared plus b squared minus 2ax. So c squared is a squared plus b squared minus 2ax. Now we got to figure out what x is, I guess, here in terms of the a, b, and c. So the cosine of angle C from this little triangle here is x over b. So from that we see that x is b times cosine of angle C. Put that back in place of the x here and we have our result that c squared equals a squared plus b squared minus 2ab cosine of C. Okay, now let's look at the next case. The next case is when we have point D is out here. So C is actually between D and B, and we have this situation here. So that's going to make angle C a obtuse angle. Angle at D is a right angle. And so this red angle you see here, angle ACD, is pi minus whatever C is for that angle. Okay, and in this case we're going to let x be the distance from D to C, and then we know it's a from C to B, so we get a plus x from D to B. Okay, and that's basically what we've said here in the first paragraph. Now, once again, we have two right triangles. One is ADC, this little one, and then the whole big triangle on the outside is also a right triangle, ADB. So we're going to apply the Pythagorean Theorem to both of those. Going from the little triangle first, ADC, we get b squared equals h squared plus x squared, or b squared equals x squared plus h squared. From the big triangle, we get c squared equals a plus x squared plus h squared. So that's just the Pythagorean Theorem applied twice. Once again, let's see. So we have this one. We're going to solve for h squared. H squared is b squared minus x squared, and put that in place of the h squared in the other one. Very similar to our last case. So we're going to put b squared minus x squared where the h squared is in this expression. Once again, we're going to use FOIL and expand this out. So we've got a squared plus 2ax plus x squared plus b squared minus x squared. And again, the minus x squares cancel. Again, we get c squared equals a squared plus b squared plus 2ax. And let's look at this. Now look at angle C. The cosine of pi minus c, this angle right here, is adjacent or hypotenuse, so that's going to be x over b. So x is b times cosine of pi minus c. But remember, in general, that cosine of pi minus c is the opposite of cosine of c. So this red angle here and this one here, the green angle is going to have a negative cosine, the red one's going to have a positive cosine. But they're going to be opposites of each other. So x is the opposite of b times cosine of c. Plug that in place of the x here. That minus is going to make that into a plus, of the plus into a minus, excuse me. And so I get c squared equals a squared plus b squared minus 2ab cosine of c. So one more case to consider. And this time, if b is the one in the middle, so c, then b, then d, and we're out here, very, very similar to our last case. Once again, we get two right triangles. This time we're going to let x be the distance from b to d. Of course, we know this is a, so this is a plus x. So it works very much like last time. Pythagorean Theorem applied to the big triangle. B squared is a plus x squared plus h squared. Little triangle here on the right is c squared equals h squared plus x squared. Once again, as before, solve for h squared. H squared is b squared minus a plus x squared. Put that in place of the other one here. And we're going to have to expand out. Now when I expand here, I'm going to FOIL and then I'm going to distribute a negative 1. So I get a squared, but that's going to make it minus a squared. I get plus 2ax, and the minus makes it minus 2ax. I will get plus x squared, and the minus makes it minus x squared. Again, the minus x squared and the plus x squared cancel, and we get this here. Now let's look at angle C. Angle C, from the big triangle, the cosine is a plus x over h, over b, excuse me. adjacent over hypotenuse, a plus x over b. Okay, and so we have that. So let's see what we can do with that. Multiply both sides by b, and a plus x equals b cosine of c. So x is b cosine of c minus a. Now we got to put that back up here. B c squared. Let's see, where are we? X, where the x is. Put b cosine of c minus a in place of the x. So we've got c squared is b squared minus a squared minus 2a times the x is b cosine of c minus a. Alright, we've got to do a little work here. Distribute. C squared equals b squared minus a squared minus 2ab cosine of c plus 2a squared. Now 2a squared minus a squared is plus a squared. We got a plus b squared. We got a minus 2ab cosine c. So in every case we obtain the following conclusion, that c squared equals a squared plus b squared minus 2ab times the cosine of angle c. Notice that we use the Pythagorean theorem in every case of this proof. So notice that if we let c be pi over 2 is 90 degrees, the last term is 0, and we have the Pythagorean theorem. And so this contains the Pythagorean theorem within the law of cosines. So you might be tempted to say, well, the Pythagorean theorem is a special case of this, and in a way it is, but it's more properly said that this is an extension of the Pythagorean theorem, because we had to prove the Pythagorean theorem first, because it was a major step in the proof of the law of cosines. And so we must have, and do have, an independent proof of the Pythagorean theorem before we can prove the law of cosines. This sketch includes a couple of proofs of the Pythagorean theorem way back earlier. So this basically takes what we could do with the Pythagorean theorem and lets us take that and use it now, not just for right triangles, but for any triangles. So you can think of it, this is sort of like the Pythagorean theorem adjusted for non-right angles, because this angle C there and this term make the adjustment. Now let's take a look at it a little bit more. So we've proved that c squared equals a squared plus b squared minus 2ab cosine c. So the first thing we can do is we can solve this for side c, and we see that side c equals the square root of a squared plus b squared minus 2ab cosine c. So if you know little a, little b, and angle c, that is, you know two sides a and b and the angle between them, angle c, that's the side angle side condition, you can plug those numbers in this formula and solve for the missing side c. Now since our original labeling was arbitrary, when we can relabel things if we want. So remember, for Pythagorean theorem, we always made sure c was the hypotenuse, and angle c was your right angle. But here it didn't really matter if it was a right angle or not. Remember, our proof went over all the different cases. So we can permute or switch around these letters if we would like. So we can change the letters around. So this last one says c equals the square root of a squared plus b squared minus 2ab cosine of c. But we can switch the letters, say, b and c here, and change the c to a b. Then inside that changes c to b here, and it changes angle c to angle b. Or we could change, say, from b here to here, change angle side a to side b here, and then it changes a to b here, and it changes angle b to angle a. So notice that you always have, if this is solving for side a, of course it won't have a side a on this side, it'll have b squared and c squared, minus 2 times b and c, but then it'll have the cosine of the angle a. So notice the side you're looking for, the one you don't know, is the one that's opposite the angle that you do know. So this will, regardless of how you have it labeled, if you know two sides and the angle in between, this law of cosines will allow you to find the length of the other side. Now, if we take our original expression, c squared equals a squared plus b squared minus 2ab cosine of angle c. This time I want to solve for the angle C. So I'm going to get a squared plus b squared. I'm going to subtract c squared, and I'm going to add 2ab cosine of c to get these terms on these sides like this. Now I want to get cosine c by itself, so I'm going to divide by 2ab to get this next expression here. Cosine of angle C equals a squared plus b squared minus c squared over 2ab. And now to find angle C, I do an inverse cosine, or arc cosine. And so C is the arc cosine of a squared plus b squared minus c squared over 2ab. Once again, we can switch the letters around if we want, permute the letters. So this allows us basically to solve for any angle if we have all three sides. So notice on the right side, in all three versions of this, we have to know all three side lengths, but you can use this then to find the three angles. And so this is to be used then in when we have the side condition. So what we have here is angle A is the inverse cosine of b squared plus c squared minus a squared over 2bc. Notice that the numerator has everything squared for the sides, but the one that's opposite side angle A has a negative and the other two are positive. And notice A is missing in the bottom. It just has 2 times b and c. And then down here, similarly, angle B, it's going to be the inverse cosine, the b here, so you got a minus b squared here, and there's plus a squared and plus c squared, and you got 2ac, no b in the bottom. No c in the bottom here, minus on the c squared. And so you can use this to find, to solve triangles. So, you know, when we were back in earlier unit, the first unit, we talked about these conditions, the side angle side condition, the side condition, and we said, oh, you know, no matter what side lengths you give me for a side and an angle and a side, there's always exactly one triangle that size. And we solved some of these by construction, by drawing them, and approximated the solutions that way. But here we see that we can find exact solutions, and law of cosines allows us to solve for that missing side. Once we have all three sides, then we can proceed like this down here in the side condition and find angles. If we have the side condition, as long as the triangle inequality is satisfied, we can have, this will compute the angles. When the side does not meet the triangle inequalities, you'll be trying to take the inverse cosine of something that's either less than -1 or larger than 1, and this will give you an error message. Okay, but if this is done correctly, it should work out. One more word of warning: be sure when you're putting this in your calculator that you put parentheses around the numerator and parentheses around the denominator. So we can use the law of cosines to solve triangles.